All right, welcome. Over the next few minutes, we're going to dive into a topic that's honestly fundamental to pretty much everything you'll do in your pharmacy career: colloidal systems.
Okay, so let's jump right in with a question. You've seen it a million times, right? Some liquid medicines are kind of cloudy, but they seem to stay perfectly mixed forever. And then you have others that you have to shake, or you'll get the wrong dose. Why is that? Well, the answer to that question is a huge deal when it comes to making effective drugs.
You know, the secret to all of this lies in the world of the really small. It's all about how these teeny tiny particles behave when they're just kind of hanging out, dispersed in another substance. They create this special state that's, well, it's not quite a solution, but it's not a suspension either. It's something in between.
And that is what we call a colloidal dispersion. Look, getting a handle on this concept, it's totally non-negotiable for a pharmacist. I'm serious, because it controls everything, from a drug's shelf life to how well it actually gets absorbed by the body.
So, okay, how do we even begin to make sense of this hidden world of particles? Well, the first step is to learn how to classify these systems. If we can group them, we can start to predict how they're going to behave.
All right, the most straightforward way to classify them is just by looking at the physical state of their parts. Think of it this way. It's kind of like making hot chocolate, right? You've got your dispersed phase, that's the chocolate powder, and you've got your dispersion medium, that's the milk you mix it into. So all we have to ask is, are these two parts solid, liquid, or gas? Simple as that.
Now, this chart is really cool because, well, it's basically a menu of all the pharmaceutical dosage forms you're going to work with. You see liquid in liquid, bam! That's an emulsion, like a lot of creams. You see solid in liquid? That gives you a sol, which you can think of as the stable, non-settling cousin of a suspension. This table, honestly, it's your first go-to tool for figuring out what kind of formulation you're looking at.
Okay, so beyond just solid, liquid, or gas, we can get a little more specific. We can also classify them by looking at the particles themselves. Like, what are they actually made of, and how do they form?
First up, you've got multimolecular colloids. The best way to think about these is like a crowd forming at a concert. You have a bunch of tiny individual molecules, way too small to be colloids on their own, but they all clump together and suddenly, boom, the group is big enough to be in that colloidal size range.
Then you've got the total opposite, macromolecular colloids. These are the big shots, the heavyweights. We're talking single, giant molecules, things like proteins or starch, that are already big enough to be colloids all by themselves. They don't need to team up with anyone.
And finally, this is a really clever one, we have associated colloids. At low concentrations, these things just act like normal dissolved stuff. But once you hit a very specific point, we call it the critical micelle concentration, they spontaneously get together and form these cool, organized structures called micelles. This is the magic behind how soaps and a ton of other surfactants work.
So while all those ways of classifying are super useful, this next one, this is probably the most critical one for you as a future pharmacist. It really all boils down to one simple question. Do the particles and the liquid they're in like each other, or do they hate each other?
And that right there is the huge difference between what we call solvent-loving or lyophilic colloids and solvent-fearing or lyophobic ones. Lyophilic systems like gelatin mixing in water are super easy to make and are usually really stable. But lyophobic systems, man, they have almost no attraction for the liquid they're in. This makes them inherently unstable, and you have to use special tricks to keep them from clumping up and just falling apart.
Okay, so now we know how to classify them. Let's get into the fun stuff. What makes them so unique? Let's talk about their superpowers, the special properties that make them behave in such interesting ways. These are the things you'll actually see and measure in the lab.
First up, let's talk about how they interact with light. This is something you can literally see, and it's a super important diagnostic tool. See, unlike a true solution, which is crystal clear, colloids do something really distinct when you shine a light on them. And it's called the Tyndall effect. It's simple, really. If you take a laser pointer and shine it through a true solution, like salt water, you won't see the beam inside the liquid. But if you shine it through a colloid, the particles inside will scatter the light, making the beam's path totally visible. It's a quick and dirty, but powerful way to confirm you've got a colloid on your hands.
Next up, their kinetic properties. The big takeaway here, colloidal particles are never still. They're in a constant state of random, chaotic motion, and this movement is absolutely essential for keeping them stable.
This perpetual random dance is called Brownian motion. So what's causing it? Well, it's the molecules of the liquid itself, the dispersion medium, constantly slamming into the colloidal particles from all sides.
This nonstop jiggling fights against gravity and keeps the particles suspended, preventing them from just sinking to the bottom of the bottle.
Okay, and finally, and I'd argue this is the most critical property for stability, we have to talk about their electrical properties. This is where we get to the real heart of why some colloids can sit on a shelf for years, while others clump up and fail in a matter of hours. And it all comes down to electrical charge.
So this whole idea boils down to a concept called zeta potential. The easiest way to think about it is like an invisible electrical force field that surrounds every single particle in the dispersion. And the strength of that field is what decides if two particles that bump into each other will stick together or bounce right off.
And this chart just lays it out perfectly. A high zeta potential, and it doesn't matter if it's positive or negative, means those particles have a really strong repulsive force. They're basically pushing each other away, which leads to a super stable, nicely dispersed system. But a low zeta potential, that means the repulsive force is weak and the particles are much more likely to stick together, form clumps, and eventually crash right out of the dispersion.
So, what does all this theory mean for you when you're actually designing or dispensing medicine? Well, it means you have this incredible, powerful toolkit of scientific principles that you can use every single day.
Think of this as your 4-step game plan for any formulation you work with. Step 1, identify the system. Is it a lyophilic sol, a lyophobic emulsion? What are you dealing with? Step 2, assess its stability. That's where you'd look at something like its zeta potential. Step 3, predict its behavior. Is Brownian motion going to be enough to keep it stable, or do you need to add something? And finally, step 4, use all that knowledge to design a product that's safe, stable, and actually works.
So why should you care about all this? Because literally every single point on this slide translates directly to patient safety and health outcomes. A stable formulation means the patient gets a predictable, correct dose every time. Good bioavailability means the drug does what it's supposed to do. You see, understanding colloid science isn't just about passing an exam. It's about being a great pharmacist who delivers the absolute best care possible.
And from here, honestly, the possibilities are endless. The principles we've just zipped through, they aren't just old facts from a textbook. They are the active, living, breathing building blocks for real innovation in pharmacy, everything from targeted cancer drug delivery to new vaccine technologies. So the real question is, what are you going to build with them?